tell HDDR, go there instead of out on the TCP stack to find the URL. That returns an object that it's a list, an R list, and it has a content member. So we grab that, we convert it to char from raw, and then use JSON lights from JSON method, function rather, to turn it into a JSON, or turn it into a list from the JSON structure. And then there are a whole bunch of list columns that from JSON produces out of this. So you need to get rid of those because when you could just create a data frame. I like working with Tibbles, so if you try to feed that structure into as Tibble, it doesn't like it because there's list columns in there that it can't resolve. So you have to remove those. And then the repo tags, because an image can have multiple tags, that's going to be a list column that for some reason as Tibble likes. I didn't really dig into this that much. But you can unnest it, so PERS unnest method will take a list column and basically expand it, so flatten it out. And then you can just use grepl to filter for where the repo tags have shiny in the name. To run this, so to do this in container, and that's what we're kind of about here. And sorry you can't see the whole command, but so I've now run an interactive R prompt, and I've bind mounted the API endpoint socket from my Docker host into this container, which interestingly enough doesn't require privileged access. You can mount any file you want in your host file system into the container, and we'll talk about mounts here in a second. But that's what's accomplishing that. So it's basically making the var run docker socket that exists on the host available in this container as if it was in the container directly. The columns equals 250. You may find in your environment that Docker makes your interactive TTY really narrow, might be 40 or 80 columns. So for doing much R interactive work, it kind of scrunches things up. So I like to pass that environment variable in. And then you can use options width to set the width of your R interactive prompt to the same width. And it just makes things expand out on the screen. Like if you just print a Tibble, it has all that nice formatting, but if your TTY is really narrow, that's not going to get you much. Okay, so we've got this, and now if we run my little R program, so here's where you can set the width to take up the whole TTY. Okay, so again, it's truncated a bit off the side, but you can see these are the tags attached to the image, and sure enough, at least the ones you can see there all have shiny in the name. Yeah, sorry it truncates it, but otherwise you wouldn't be able to see it. Okay, so does everybody kind of get that? I mean, the whole point of this was to illustrate that this is Docker is nothing more than an HTTP API. And it's just manipulating these processes that are running in the Docker host. All right, so I'm going to accelerate things because we're a bit behind where I thought we'd be at the break. If anybody's really interested or concerned about a topic and you want to dive deeper, let me know, but otherwise I'm going to kind of go pretty fast. So the way you create images in your local registry is through Docker build, and you script those builds with Docker files. And I've listed here kind of the 80% commands that you use or instructions you use in your Docker file. And there's what each of them is used for. You always have to have a from. Everything else is optional. But you're going to use some of these, otherwise there would be no point and no reason to create a new image. You use copy to copy contents from the context, which is the directory structure at and below where your Docker file lives. So when you run Docker build, it takes everything that's in that directory structure below there and copies it into the Linux host. It zips it up and copies it in there. And then anything that's referenced in a copy command actually gets added to the layers file system, and then it discards the rest. But if your builds are taking a long time, check to make sure that you didn't copy some ISO or your whole database or something like that into the directory where your Docker file lives, because that could be the cause. You only want to put things in there that you're actually going to copy into the image, or else your builds will take forever. We'll talk about entry point and command here in a second. One thing to note that's often confusing, the expose directive in a Docker file does absolutely nothing other than document what ports you as the image author think should be exposed. It doesn't actually do anything at runtime. You still have to expose the port via the -p option when you run it to get that port to expose. It's just documentation to whoever's going to run the container that, hey, this is a port that's designed to be exposed, but at Docker runtime, you still decide whether to expose it or not. I'm going to skip going through Dockerfile examples because I think probably most of you have seen them, and we're just going to accelerate through this. So another common point of confusion is the difference between entry point and command. And there's a nice little table in the Docker documentation. If you go to the Dockerfile reference and go to, it's referenced from either the entry point or the commands section of that. It has a nice little table about what all the different options are. But in short, the entry point defines the command that's to be executed, and the command CMD instruction defines the arguments to entry point. But if you don't have an entry point, what's in CMD becomes the executable and the arguments, if that's clear as mud. So it's just a way for an image author to distinguish between the bare command that's run and arguments or options that are passed to that command, so that you could allow a user to change the arguments without changing the command, the executable that's run. And you see sort of both things depending on what the purpose of the image is. So there's really not one way to go here. It kind of depends on what you want to accomplish. And the best practice is to specify these as an array. So the form is CMD or entry point, and then in brackets, it's just like a JSON array, brackets, and then each component of it has a quoted string separated by commas. Just makes it clear and easier to read. Okay, so one of the decisions that you have to make when running network services is whether you have multiple services in one container or one service per container. So here's an example. Let's think about a Shiny app that is accessing a database. You're going to have your database server process, and you're going to have your Shiny server process. And you could create a container whose command or entry point is a process supervisor like supervisor D, or S6 overlay is what the RStudio server image uses. And that supervisor could then launch the sub-processes. And so what's actually happening there is the process that the Docker daemon launches is the supervisor, and then the supervisor runs as child processes in the same namespace, however many child services you have. And this is kind of a common approach that you see when people have taken existing kind of Unix-based applications that use the init system and transition them to containers. In my view, that's not the best way to do it. Sort of the Docker way is to have processes that don't spawn child processes. So if you're running RStudio server, have that be a container, and then have your database server be a separate container. There's all sorts of reasons for this. It's sort of have them do one thing and do it well. Also, it's really much easier to do fine-grained scaling with Swarm if you put things in, if you isolate processes in separate containers. For instance, you could have 10 versions of RStudio or 10 copies of RStudio running with one database. using Swarm. But if you put them both in the same container, you're either going to have 10 of both, or 1 of both, or 2 of both. You have to choose the same number. So it's just, mostly it's kind of a design preference, but I think if you took a survey of people who have been doing Docker stuff for a while, even though there's maybe a bit of a tussle over this, most people prefer to do the one process per container approach. But if you want an example of the S6 approach, look at the Docker file for RStudio server, because they use S6. Incidentally, in images that do this, in the Docker world, Supervisor D is probably the most common one. So if you're thinking about doing this, running multiple services in one container, look at Supervisor D. It's super easy to set up, configure. It's just a simple config file that drives it. That's what most people are using. And I don't know, Kelly left, but I don't know why RStudio chose to use S6. Maybe we could ask him here at the conference. Okay, so a quick little exercise just to kind of give you practice with Docker files. And this is maybe a common, perhaps the most common task you have for building R images. There isn't one in Rocker that has the Lubridate package installed. Just I don't think the Tidyverse one does. So create a little Docker file that modifies R 3.5.0 to, that modifies the stock RStudio image to have Lubridate be available. Okay, so take, let's take 5 minutes on that one. Okay, so the goal here is when you hit localhost 8787 and bring up RStudio, you should be able to do library Lubridate and have it not complain at you. You shouldn't see that when you're done. If you just run the stock RStudio image, that's what you're going to see. Well, remember the expose directive in Docker files doesn't do anything, it's just documentation. But the command and the entry point are inherited. And of course, you're just building new layers on top of that. So all the file system stuff that happens in the base Docker file is still there. And you're basically just taking that existing image, and your Docker file is just stacking new layers on top of it. And if you don't change the command or entry point, it just uses the command or entry point from the ones above. Well, it's not, when you do a Docker build on a Docker file, it's not rerunning the stuff in the parent image Docker file. It's just using that image as it was built. So it's pulling it. Okay, so if you do Docker, if you do from RStudio / Rocker / RStudio, it's going to go pull that image from DockerHub if you don't have it locally already. And then it's going to start executing the instructions in your Docker file. All right, let's take a look at this. I may not have made a pre-cooked version of this. Well, let's do one. Okay, and incidentally, you want to call your Docker file with a capital D, and then Docker build will find it automatically. You can call it something else, but then you have to pass -f and the Docker file name to Docker build. Okay, so we're going to do from Rocker RStudio. And then what we want to do is run an R command to install some packages. So hopefully you all are familiar with running things, with passing an R command to run in R from the command line. So you do that with -e, and then we can do install packages, delivery date. Okay. Okay, so I'm going to call my image. Just a little best practice I follow is, you might have noticed in my GitHub repo, in the Docker repo, there's a folder for each image, and then inside that is a Docker file, and then inside of that is a folder called files, and that's where I put any files that I'm going to copy into the image. I always tend to call the name of the directory that contains the Docker file the same thing as the name of the image I'm going to build. It just makes it easier for me to kind of keep track of things and find stuff. So in this case, can you pass the name of the image as the -t or tag option? Call this RStudio delivery date. And then you pass the directory that is the context of the build. So usually you're doing that from the current directory. I hope delivery date doesn't take a long time to build, otherwise we'll just kill this. Okay. All right. Well, anyway, if you all have done that, I guess you can sort of take my word for it that it would actually build. But this is kind of the, and I'll push this to GitHub. So if you want it as an example, that's pretty simple. So it's a 2-line Docker file, right? And in the R world with Docker, this is a very common thing that you have to do because your image undoubtedly has you need some packages in it that aren't in the Rocker stuff. You've built some for yourself, or you just need a particular set of things, although the tidyverse base image is a good one to use because installing that stuff really does take forever. But if you need something new, you can just do it this way. And of course, the install packages function takes a character vector, so you can just list out however many packages you need right in there, and it'll whip through them and install it. And then you can Docker run this image, and you've now got your RStudio with delivery date installed. Any questions about that? Make sense? Okay. One other little tip here. A lot of times when you're, especially if it's not something this trivial, when you're building an image, create an instance of or instantiate a container interactively using your base image. So this would be Docker run it, don't remove it. Docker run it RStudio or rocker/RStudio bash. And then get in and start running the commands that you think you're going to need to build your container. So in this case, it would be r-e install packages, whatever. And get the image to your satisfaction where everything runs, because sometimes you may not have a dependency. Some R packages require that native system libraries be installed. You may find, oh, geez, I don't have that library here, so I need to go install that. So make all those mistakes and get it all set up, and then you can use the bash history command to show you all the commands that you've run in that shell since time immemorial. And you can go through there then and copy them out, and those are the basis for your run commands in your Docker file. Okay, so it's kind of a nice way to go from just kind of building it organically from scratch to a Docker file without having to sort of keep separate notes or write down what you've done, or those kind of things. Okay, does that make sense? Just a little lesson from stubbing my toe many times. Okay, I've referenced this a couple times. The way that the Docker images work, think of it like a layer cake. And at the very bottom of the layer is the scratch image. And then from all the base images that you've built for and all the ones that those extend and all the ones those extend, we've just added layer upon layer upon layer of file system and configuration to this image. And when you run Docker build with the Docker file, you're just adding more layers on top of that layer cake. And then ultimately, whatever the last layer is the state of the container when it gets run. Okay, so this is what did I do? I did the Rocker RStudio image. So you can tell all the sequence of steps that went through building that. So there you go. Those files actually are other images. I'm pretty sure. No, they're not. Yeah, so actually the history just shows you the history or the layers of that very image, and it doesn't show you up the from hierarchy. So those add files are just where the Docker file that the Rocker project folks built, that's where it's copying files into the file system. And you can just sort of see all the things up the chain there. Yeah. So everything that you do in a Docker file, unless you use a user directive, is done as root. Okay, and this is a good question. If you're wondering about the security of that, like I said, I've been doing Docker for 3 years, and including some production contexts in the criminal justice system where security is pretty paramount. I have never once created a Docker file that does anything other than the root user. The reason for that is the harm of someone getting into a container and doing stuff as root. They could muck around in that container, but that's about it. Okay. Where you really control your security is how you run these things. So these processes are running as root in the host, but they don't have very much permission to stuff or access to stuff. So it's really pretty, and usually your Docker host doesn't and shouldn't have anything, any kind of state in it. Any kind of important state should be stored in volumes, which actually can live in places that you can protect more, with better permission. Yeah, right. Yeah, so if you do change the user, then yeah, that could cause you problems. So in your derived image from RStudio, if you change the user that it runs as, it won't find the packages. It won't find packages that were installed by the root user higher up or lower down in the layer cake. Okay, so you can use, Docker images tells you how big these images are. So there's a couple things here. So the size of the RStudio image is 1.09 gig. When you run an instance of it, so this is a container like the ones we just ran, it'll tell you the virtual size of it and the size of the layer. So when you run a container, the file system contains all this stuff, but then it also contains another layer that the container can write to. Okay? And when you look at the size of the image, it'll tell you what that last container size is. So whatever RStudio is doing, and I may have run this after I actually did some stuff in a container. It's 25 meg seems like kind of a lot of stuff. But it's probably writing some log files and some other things, and maybe when R starts up, it's doing some stuff that writes things to disk. So anyway, that gives you a little bit of information about the size if you're running this on a Docker host that doesn't have a lot of disk space. Okay, and each one of these layers is stored as a separate entity in the Docker host. So a common thing that happens as you're running Docker build is your build will fail at step 12 of 20. And so you'll fix step 12 and rerun it. You'll see as Docker build runs by, it'll say using cache, using cache, using cache for the first 11. Because at each step, each instruction in your Docker file, it's writing that layer out to disk with a hash tag. And it'll reuse those when it can. And the hashtag is formed from the text of the command, not its results. So that's important. If a common thing that you'll do in a Docker file is go out to the internet and curl something in, like if you need a library or just something from the internet, you can use curl to go out and pull that thing into your images file system. And maybe that's some library that's produced by a business partner or some other department in your organization. If they go change that and push a new version of it, your Docker file won't pick that up, or Docker build won't pick that up, because what it's using is the text of the instruction in the Docker file. So that text doesn't change, and it has something for that hash in the cache, it'll just use it. If you want to override that, you can pass the -no-cache option to Docker build, and it'll just ignore all the cache stuff and rebuild it all. Okay, but you obviously want to use the cache when you can if you're in Docker image development mode, because maybe some of your earlier steps take a long time to build. Okay, a real quick thing about documentation. The label instruction is new as of a couple of Docker versions ago. And this is really nice because all this stuff shows up in Docker info, so you can query for images and subset it for various metadata elements. And the most common ones you should use are maintainer and description. VCS URL, which is the pointer to where the source code for the Docker image lives, is a good one to use as well. And the community is sort of converging on using label schema as the sort of canonical reference for metadata for container images. So it kind of defines a common vocabulary so that when we put these things in our Docker files, everybody knows what the things mean. So I would encourage you to use those attributes when you can. Pushing to DockerHub. So when you do Docker build, even if you use your DockerHub account as the prefix before the slash for the image, it's still just living on your machine and it's not up on DockerHub. If you want it to be up on DockerHub, you have to do Docker push on it. And so the format of the command is here. I mentioned earlier that if you first build an image and then later on you change your mind and decide to have it available on DockerHub, you don't have to rebuild it. You can just use Docker tag. And it's, so Docker tag and the existing image name. And then the second parameter is the new tag that you want to give it. So this works sort of like tagging in version control systems. It just gives it a new name, or an additional name, I should say. But if you do Docker push and it's a qualified name with a DockerHub account as the prefix before the slash, it'll actually make sure that you have access to write to that account on DockerHub, and then it'll just push it up there. So this is how the Rocker folks publish theirs. It's how I published the ones that you pulled down this morning, and it's how you make them available for other people to use. Okay, and go out and explore around on DockerHub. You'll see some examples of how to do documentation. The first page of an image on DockerHub gives you a little short description and then a bigger description where you can document what that image is. And it's just Markdown, so you can use Markdown syntax to help people understand how you use your image. Okay, volumes. So as we've talked about, when you create a container and that container writes data to the container file system, when you blow away that container, all that data goes away. So the sort of intended way of being able to persist data both across containers and to save data that should be persisted after the container process ends is to use volumes. And there are two types of volumes. Actually, there are three, but I don't really know anybody who uses tempfs volumes. So just focus on bind mount volumes and volume mount volumes. Bind mounts allow you to give a specific directory on the host where the data will be written. So if you have a particular place that's tied into your backup system, or just have some reason why you want something written in a particular directory on the host, use a bind mount. If you want Docker to manage your volumes in a data structure that's somewhat hidden from you, although still accessible, then just use a volume mount. If you use a volume instruction in the Docker file, it will create, by default, unless you specify different at runtime, it'll create a volume mount for you. So if you put volume myvol in there, it'll create a directory at the root of the container file system called that, and it'll be a volume mount that's stored inside Docker's application data structure in the host. So those files are still accessible to you. They're just not in a place that you can specify. And so the way you do this is with the mount option at runtime, and it takes a string. I didn't put it in quotes, but when you actually do it, you should put what follows the mount option in quotes. And it's 3 comma separated parts. The type, and the type is always either bind or volume. And then the source. For a bind mounted volume, it's the directory on the host. For the volume mounted volume, it's the name that you want to, the name of the volume that you've already created, or it'll create it for you if it's not existing already. And then the target is the path in the container. Okay, and here's the place down inside the Docker application structure where it keeps these volumes. So let's look at this real quick. So there's a volume command, so Docker volume ls will tell you all the volumes that you have, and so there's a lot of these because a lot of the images that I have volume instructions in the Docker file. So it just creates these random ones that are unnamed in the data structure. But at some point I did a Docker volume create foo, and it created that volume called foo. And if I go into my Docker host, where was my command? 636. So if I go into var, so again, I've used that little trick with nsenter to SSH into the host. If I go into varlib docker, and I go into volumes, there's a directory called foo there. And at some point I put a file in here, I can't remember what it is. Oh, I must have deleted it. But when I did docker volume create foo in my Docker host, it created this directory. And then in any image that has that volume referenced, or if I mount a volume at runtime to that, any data that's written into that directory in the container will be written in here, and it'll be persisted even after you remove containers that use it. You can use Docker volume RM to get rid of this directory, but typically these are things that directories where you place data that you want to stick around. And you can even tie this into your backup system, right? So you can just back up the varlib Docker volumes directory or specific subdirectories if you're storing database data or whatever in here. All right. And so a bind mount, you saw this when we bind mounted the socket. Down here at the bottom. In addition to doing mount points that are directories, you can mount specific files as well. And this is how you do it. And notice that I specified the type of bind here because I wanted to reference a volume at a particular place on my host, not one of the Docker managed volumes. All right. In the interest of time, we're going to skip this exercise, but you can come back and do this later if you want. It's basically just getting practice creating a volume. All right, so networking. Most of the things we do in Docker involve networking. So inter-container communication occurs over networks that Docker manages. So if you have, again, our example we've been using of a Shiny server in a database, they will communicate over a network. And then we've already seen how you can expose ports. You can open holes in Docker's firewall to expose ports that are running on those internal networks as if they were exposed on the Docker host. And then Docker for Mac and Docker for Windows and Docker Toolbox all have mechanisms where you can make those ports available on the host. Okay, so the default network type in Docker is a bridge network. The other type you would use is overlay networks if you're running Swarm. And really a Swarm overlay network is just a bridge network that spans multiple hosts, and they're just connected by a VPN, essentially. And then also on a bridge network in Docker, there's automatic DNS resolution by the container name. So if I have a bridge network that I've created, this doesn't work on the default bridge network, but if you create a bridge network and put containers on that network, they can all access each other by their container name as their host name. Okay, so let's say in our example we have our studio or a Shiny server and a database. They can talk to each other by their name. So when you get a connection in Shiny to the database, you would do it by using the name of the database server as your host name for your database connection. And so here's sort of a picture how that works. Again, the default bridge network, which is what, like when we ran our studio image and when we ran our interactive R containers, if you don't tell it otherwise, it's starting those containers on the default bridge. But you can create a network with Docker network create and then give it a name, and that creates a bridge network. And then you can use the -- network option on Docker run to put those containers on that network. And I've got those commands here. So it's just real simple, Docker network create and the network name, and then when you run it, you put the container on that network by specifying it with the network option. Okay, and so containers can only talk to, and not just name resolution, but actually the IP spaces, the IP address spaces, are constrained only to a network's own bridge network. So if I create two networks and I have containers 4, 5, and 6 running on one and 7, 8, and 9 running on another, they cannot connect to each other. They can't talk to each other. they have different IP address ranges. So it's a useful, nice way of kind of isolating things network-wise. All right, one of the useful options that you can pass to network create is a definition of the subnet. And you do this typically if you have multiple networks that you need to run, and you want to sort of organize how your network space, so your IP address space is partitioned. Also, in the multi-container example I have for you, there are some configurations in there that where you're required to specify the IP address. So sometimes when you run a container, you actually need to know what the IP address of the container is, or at least what the subnet is that it's running on. And so if you want that fine-grained control, then just put it on a network where you specified the subnet at the start. Okay, so there's a command, an example of running RStudio on this network. If you're not really familiar with TCP/IP networking, if you haven't done much of that, come back to this slide later. It tells you a little bit about how to specify networks. It's all done with CIDR notation, which allows you to define these IP address spaces. You should always run create your networks with private IP address spaces, and these are the private networks that are defined in IPv4. So hopefully these would be enough IP addresses for you. If not, then maybe think about v6. But the CIDR notation, everything after the slash tells you the number of bits from the left of the address that are fixed. So, and you can fix things further. So if you just wanted the last digit of the IP address to be flexible, which would give you 254 IP addresses because the first one and the last one are not available, then you would do /24, which means that, well, you'd specify something other than 0 in the third part, and then all the addresses would be the first three numbers, and then the last would give you 254 to play with. So it's just a quick way of defining subnets for your containers to run on. Well, you'll see that with the multi-container example that I have. But really, when you're running things other than just kind of playing around, you should always create a bridge network. Yeah, so you only need to specify subnets if you need to control this for some reason. I'm not sure what Docker does by default, but if you're running lots of networks or have lots of containers, you may want to tighten down and just have more control over the subnets. And then, like I said, in some cases, the applications that you're running, the processes you're running in the containers, need to be configured. Maybe they have security settings that are using IP-based access control, and so you may need to know, hey, I only want this range of IP addresses to be able to access this thing. And so to be able to put that in your configuration file, you need to have set up a network that is on that uses that subnet. You know, frankly, it's pretty rare to need to muck with this stuff, but if you do, there you go. Okay, so let's do this real quick. So I've set up an image for you already called, in my repo, tidyverse-mariadb. And so let's run that container and expose it on port 80 if you want. If you want to just use 8787, that's fine. I suggested port 80 if you want to get practice with exposing ports or mapping ports. Okay, and then on the same network, run a detached instance of MariaDB, which is MySQL. So if you're working with SQL databases, this is a common one to use. And I've set up an image for that as well that you hopefully pulled down earlier. And so give these two containers these names. And then get into your RStudio session that you just created. And so and then get a connection to the database. And see if you can get the contents of table T1A in the database that's kind of pre-baked into that image. Okay, so there's kind of 4 tasks here. Create the network, and I would suggest calling it that. Run your RStudio server on that network. Run your database on that network, and then see if you can open up a connection to that from RStudio. If you haven't done much with DBI, I don't know if you can see that. Just to shortcut it for you, if you don't work with DBI a lot, there's a function in DBI called dbconnect that gets you a database connection. And you specify a function, or you call a function that creates a hook to the driver, which in this case we're using the MariaDB driver. And then there's 3 parameters you need to pass in: the host, the database name, and the user. So all this stuff is all specified in the exercise, but just to shortcut you a little bit. Okay, unfortunately, we're going to have to get going here. So let me work through these steps here. So to create the network, create network user. And hopefully that was straightforward for you all. And then we're going to run our RStudio image. detached. We're going to use that network. We're going to expose 8787. Oh no, we need to use my image, don't we? Sure. You can do 80 if you want, sorry. Okay, so we've got our studio running. Now we need to run our database. Click demo. Okay, so we have both running now. Oops. Okay, so of course the default RStudio doesn't have the MariaDB driver in it, but hopefully, so the reason it's available here is because I did what we did in the Lubridate exercise, except I installed the MariaDB driver, DBI driver. And one interesting thing about that is it requires a system library. The MySQL client libraries to be installed. So there's an extra step there where you have to use apt-get to install those libraries in the image, not just the R package. Okay. So let's create a connection to our database now. And our host is the name of the database container. Our DB name is demo1, and our user, is root. And then we can do DB read table, and you pass in the connection and the name of the table, which I said was what, T1. Okay. All right, so what did we just do? We demonstrated if you run into a task where you're provisioning RStudio for some analysts or data scientists, and the data sits in MariaDB or MySQL or Postgres or whatever, the database doesn't matter. There's Docker images for all of them. You can do a multi-container application here, run it on a bridge network, and have them be able to talk to each other. Interestingly, so there was a bonus part of the exercise. Let me just show you what that is. So the MariaDB, the stock MariaDB image has all the MySQL client tools on it. So you can do okay, so I just ran the MySQL client. I don't have MySQL running sort of in native mode in the Docker host. It's only running in a container. So we actually need to try to connect to it. So now it gives me a different message, which is, I don't know what that server is. Does anybody know why I got that message? I've got containers up and running. We just connected to it from our studio. Right, we're running on the default bridge network, not the network that has that database on it. So Docker's doing a good job of firewalling for us. It doesn't allow that access. So if we now do WZAR, now we get in. And so you can do show tables, databases, and use demo 1, show the tables in there. We can do select star from table 1A. That's the same results that we got in the RStudio session. Okay, so just showing you that the, whoops, I'm still in R mode here. Just showing you that the networking actually does work. Okay, I had an exercise for Swarm, but in the interest of getting to the, I want to show you the multi-container application, and then I want to show you some of the GPU stuff in the 20 minutes we have left. We're going to skip the Swarm stuff, but in short, what this allows you to do is run your containers not just in sort of basic mode, but run them in a Swarm cluster. And the command that you use for doing that, well, you create a swarm with init, which takes the host, the Docker host that you're currently running on, the Docker daemon that you're accessing, and it initializes a swarm, which basically starts up a bunch of stuff that allows replication and load balancing to happen. And then once you, on the Docker host where you init it, it automatically joins the swarm, but then you can have other physical or virtual Docker hosts out there, and you use the Docker swarm join command to join that swarm, and it makes those Docker hosts appear as if they're virtually part of the same cluster, so that when you create services on that swarm, it will load balance and distribute the instances of the containers across those physical nodes or virtual nodes, across the nodes in the swarm cluster. When you create a service, and Docker Service Create is basically, has most of the same options as Docker Run, and it's kind of the same thing. You're basically instantiating an image as a container, but it has a few extra goodies, and the one that you're most likely to use most often is the replicas option, which tells Swarm how many copies of that container to create. So in this example, we used 4. What it'll do is take all of the nodes in the swarm, and it could just be your one node that you initialized off the bat, and it'll always make sure that that number of copies of that container are running, and that it load balances requests across them. So let me just do something quick here. So I have a swarm that I've already created, and let me create I'm just going to do this example that I had set up. So this Shiny image that I built is, and you can look in GitHub at it, it's basically an instance of Shiny server that has some little Shiny applications in it. And one of them is one that oh, I didn't expose the port, did I? what is it, 38? 38? Yep. So it takes a little while for Swarm to run things because it's actually creating a little bit more glue around the containers than just running it. And now we have our Shiny, so we have a little Shiny application running in this container. And remember, I started up 4 copies of it, right? So all this Shiny application is doing is calling out to the system call that gets you the host name of the current machine. I can't remember what it is. And it's also getting the IP address. So you can look at the R code in the Shiny app for how this works. But as I refresh the page, you can see that it's coming from a different host. And you can hear that I'm refreshing here. So what's happening as the browser's going to the Swarm and hitting that port, Swarm is load balancing the requests as they come in and hitting each one of those 4 containers in round robin fashion. And it's all running on my MacBook here. So this is one way you can run multiple copies of RStudio or Shiny Community Edition, but have it scale better than the default one does. I think the enterprise one you can pay for the capability to basically launch as many R processes as you want within Shiny. Well, this is a way to do it just using the stock Community Edition one, and it'll load balance them. Okay. So again, look more at the code if you're interested in that. Okay, Docker Compose really quickly. So as you create applications that involve multiple containers, you can use Docker Compose to sort of script how those things start up. So instead of running Docker run for each one of your containers that you need, you specify the run parameters in a Docker Compose file. And then it will run all of those as if it's sort of a script. Okay, so we were going to do an example of this, but I really want to get through some of these other things, so we're going to skip that. And we won't be able to go into too much depth on this either, but if this is of interest to you all, I'd encourage you to look at it after the session. So one of the things I have to do in my work is gate access to things. So we have users that need to access applications, but we want to control who's accessing it. So we want to provide sort of credentialing and login capabilities. There's an R package for Shiny that will do this, where you actually create credentials essentially in a configuration file, and it will it'll use that and prompt the user to log in. One of the problems with that is usually users have an existing set of credentials, and it's a real pain for them to have to get another account to have to remember, and then somebody has to manage those credentials and take care of revoking them when people should no longer have access and all that stuff. So there's an open standard technology called SAML, Security Assertion Markup Language, that developed protocols for federating identities. So it's sort of a precursor to OAuth. If you've seen OAuth used, where you go to access a service on the internet and it'll offer you the opportunity to log in via Facebook or Google. It's sort of similar to that, but different in that it's a lot more powerful and it gives you a lot more control. So there's an open source implementation of this standard called Shibboleth that was developed by a university consortium, which I think is international. Most of them are in the US, I think. And the architecture is fairly simple. So you have an existing set of credentials, like in an LDAP directory, like Active Directory or Open LDAP or whatever. And there's a component called an identity provider that's responsible for authenticating users using that. So this identity provider in the directory sits in the organization that has the existing credentials. So if you're just one department or one organization, it would be your existing one, but you can also federate this out to partners, and each of them would have their own identity provider that authenticates the users that they manage. Then the second side of the protocol is this service provider that's essentially an authentication gate that sits in front of the application, And when a user tries to hit the application, in our case it's going to be a Shiny application, the service provider detects that they don't have a session. We don't know who this user is. So it uses browser redirects to redirect that user to the identity provider, and it prompts them to log in. So they log in, type in their user ID and password, assuming that it's correct against the LDAP directory. It pulls whatever attributes you want out of that directory and forms an XML document that gets digitally signed as an assertion about that authentication event. And then again, through browser redirects, it sends that assertion, that token, back to the application, says, okay, thank you, I recognize this, I can check the digital signature on that document to make sure that this is authentic, and now I can let that user in. And I have in that assertion some various information about them, like maybe job roles or training that they've had or privileges that they have, membership in organizations, whatever it might be. And I can use that as a basis for customizing or personalizing or applying access control in my application. Okay? So all these things are open source, and I've created Docker containers or Docker images for containers that do all of this that you can use as a basis for doing this if this is of interest. Just a little bit more about SAML. And so rather than go through this, because we really don't have time, there's a Docker Compose file in the root of the Docker directory called Secure Compose, or no, it's just Docker Compose. It has all of these components in it. And so if we just run this, okay, so it doesn't like that because I created well, we'll just force it for now. Oh, it doesn't let you do that stupid thing. I wonder if that's, yeah, so yeah, I don't know which, it's the NWUSR one that it's not letting me remove. I don't know which one it is. So what you can tell which containers are on a network by doing inspect, and it'll tell you. Oh, I guess it's my MariaDB one. Okay, now we should be able to do this. Okay, so this is Docker Compose in action. It's going through those and creating containers for all of those little components in the multi-container application that I showed you. So let me just show you what this looks like. So in the browser, if we hit and I mapped it to port 80 incidentally, so. And the reason it's giving this is because I've just used self-signed certificates. Uh-oh. What's that? No. Oh, bummer. No, it's not. It's not that. Well, I don't want to dig into this now because I want to get to some of the GPU stuff in the 5 minutes we have left. I, is it 12:30, Nick, or 12? Really? Yeah, you know what? Let's come back to this though, because I know some of you had an interest in the GPU stuff. I'm sure. No. Well, hallelujah. I got a few more gray hairs now. Okay, yeah, let's come back to this because I want to get to the reproducibility stuff and show you how to run some of this stuff on EC2. I'm sure that's just some little thing that if I slow down and take like 30 seconds, it'll be immediately obvious what it is. So let's, in fact, I think I already know what it is, but let's just keep going here. The ROpenSci folks have a really nice little guide on reproducible research. If that's something that is of interest to you or something you need to do, I'd highly recommend it. But as I was thinking, I did the little survey that you all were, or many of you were gracious enough to fill out, and you mentioned reproducible research on a lot of it. And it's not something that's actually been important, really, in what I've done necessarily. So it was a great chance for me to get my head into it and find out what people who have thought about this a lot have had to say about it. And it seems that what I was able to kind of glean from it is that there are layers to it, that you think about being able to reproduce what you've done, some results that you've produced in terms of the layers of how you got to your results. So obviously at the bottom of any kind of effort to produce analytical results is some kind of computing environment that you've set up to run this stuff in. And that, I think, is where Docker can help you with reproducible research. So they talk about, and maybe I can submit a PR to add a paragraph or something about Docker here. They talk about it in terms of virtual machines, which is a very useful way of doing this. So you would, create an Ubuntu VM, say, in Oracle VirtualBox, and install all of your stuff, install R, install all the packages, all that. Pull your code from a GitHub repo, say, put your source data in there, or maybe your R code pulls it in real time off the internet, whatever. You've got your R source in there, and you're going to run this stuff, or you're going to run an R Markdown document and knit it, and you're going to produce some kind of report at the end. And so then you could take that virtual machine and zip it up and make it available to anybody and provide instructions on how to install this in VirtualBox. And in theory, they should be able to unzip it, install it in VirtualBox, and repeat what you did. Hopefully, if you weren't already aware, you've learned today or seen today how you can do this a little bit easier with containers. You would, instead of packaging it up as a virtual machine, you'd create a Docker file that does all that stuff. And then you'd either distribute the Docker file or you could push an image that contains all of that stuff out to DockerHub. And at the bottom of your paper or your report or whatever, just say, hey, this is all reproducible via pulling Docker image, whatever. So that's kind of how I've approached this. Compared to VMs, Docker, I think, offers some advantages for reproducibility. There's a much smaller footprint because you're running in the same Linux kernel, right? So you're not having to install all of that VM stuff and a 20 gigabyte file system and all the other things that you'd have with a VM. It's super easy to deploy. The instructions are basically Docker run -it and the image, and then maybe a little bit of instruction after that. You can even run RStudio or Shiny and create an application that does it. It's an open source platform, so it's automatically accessible to anybody. There's no licensing fees or anything that anybody has to buy to reproduce your results, assuming that you're not using proprietary stuff in your image. There's kind of community consensus around the set of Rocker images, and I mentioned earlier that if you really need to say, hey, this is reproducible on our version 3.3.2, then you can base your Docker file on that, and it'll include all the same MRAM packages and all that. So when I think about this and kind of mapping this to Docker, and these are kind of my terms, but it's sort of how I took it from our OpenSci work. There's context, data, and pipeline. So the context is that computing environment in which the analysis is done. The data is the data that you fundamentally start with, on which your analysis is done or the computations are done. And then there's a pipeline of transformations of that data from raw data and source into results. And so this is kind of how you would map this into a Docker world, I think. Your context is going to be defined in a Docker file. The definition of that could be managed in source control. So you could point people to a GitHub repository. You can version that. You can push images to DockerHub and version those images. So you can always tell people, hey, to reproduce version X of my analysis, it's based on version Y of the image, which is created by version Z of the Docker file and context that's in GitHub. So it's all real clear and deterministic how you get from A to B. For data, you can certainly distribute data as a container. So you could create an image that in the Docker file goes through and pulls all the data in and puts it in a database or just in CSV files. The image could get quite large, and so maybe this isn't practical for many scenarios, but if you really need to distribute the data, you can do so. Or just have, what I do a lot of my own work is integrate the data in the pipeline into one step. So it pulls data from various sources online or whatever, or it assumes that you've pre-downloaded data and have it in the Docker host, and that's clearly documented. But you can do all that sort of in one pipeline step. So in other words, you have one R program or script that goes to, the first part of it is putting the data together, and then a pipeline, and then processing your results. And then ultimately, especially if you're doing this in an interactive container, you probably want to offer a volume mount point where the results go, so that if somebody is going to use your stuff to reproduce the results and they're not real familiar with Docker, they don't run 3 hours worth of stuff and then have it go poof when they remove the container. So you've seen how to do things with volumes, so you can do that. Okay, so just for fun, and I mentioned kind of at the outset that I have kind of almost a hobbyist interest in elections. We've had some interesting ones in the U.S. lately, so I've been playing around with some of that. But since we're in Australia, I took a little time and pulled data from the Electoral Commission, I think, is the federal agency that manages election data. And then I think it's your Census Bureau or Census Agency that publishes shapefiles for the Commonwealth electoral districts, which I guess are different districts than you have at the state level, right? They have different boundaries. Anyway, I learned a lot, goodness. Yeah, so, yeah, well, it can't be any worse than what we have, so. One other resource that I want to point you to is, and full disclosure, I've done some work for them, so I have a business relationship with them, but knew of them before that, and it's a tremendous resource for open data called data.world. I don't know why it keeps doing that. So it's basically an open data publication platform and collaboration platform where you can publish things, publish data sets, and they have really neat collaboration features. So like if you're working in civic tech or any place where you have open data sets, you can create accounts and projects out here, and it gives you a way of sort of like GitHub for data. It actually does version stuff, and you can create, this is a data set, but if you create a project through data.world, you can actually create what they call insights, where somebody can do like a visualization of data in a data set and publish it to this, and you can get discussions going around them and kind of cool stuff like that. And they have R packages that wrap their API, so you can pretty easily integrate use of these data sets into your work. And it's all free and freely available and done in the spirit of open data, so it's pretty cool. But anyway, what I did was pre-process some of this stuff because it was a little bit messy in how it came from the federal agencies. So I had to do a little bit of munging and cleanup on it. But this is from the House of Representatives election in 2016. And it's the level of records here in both. In the top data set, it's some census variables from the 2016 census, like number of families with some number of children. There's some income variables in there and whatnot. And then this one is, oh, sure. And then the second one is the actual results. So it's by Commonwealth Electoral District, and the number of voters, the number who voted, and then the votes for each political party, which you all have a lot of those. I think we'd probably be better off if we had a lot of them too. But anyway, yeah, there's, how many of them are in this data set here? 51 parties actually were in the, I guess, officially registered or were on the ballot or whatever. Okay, so this data set. So back to kind of our context, data, and pipeline taxonomy here. I did a little Docker file that installs some stuff, installs GG themes because I like using GG themes in my plots. And you can see right here in my GitHub repo, I just did a little R Markdown notebook that takes the data you just saw, pulls it in, does some analysis of it, and then the command for this image is to run the render function in R Markdown and takes the file that I just downloaded. For some reason, it doesn't seem to work just using the URL. You know, lots of our functions that take a file as an argument can also take a URL, and we can just go pull it down. And for some reason, render doesn't do that. So you have to go curl it down first, and then run it from local storage. And then it writes the output to that notebook. I don't really remember even what this does. Oh, I know. It's sure. Yeah, I think I did it. Well, no, I did. I wrote an R script, and it's in that same GitHub repo to kind of munge the data. But the R Markdown takes the data sets you saw in data.world and produces the analysis, which we have a little time at the end. I'll show you what the analysis was. But it was just a really silly scatter plot of, what was it? Oh, it was the unemployment rate in the electoral district plotted against the percentage of, who's the ruling party? It's liberals, right? Which is actually like 3 different parties, but it's a coalition, right? So it was a scatter plot of that, and they were in power. They had the majority in the House of Representatives before 2016, right? So you would think that like the unemployment rate would be kind of a referendum on, hey, if there's lots of people unemployed in our electoral district, we might be willing to give the other parties a chance. And there was, in fact, a downward relationship. So the higher the unemployment rate, the lower the vote percentage won by the liberal coalition parties was. It wasn't huge. It was, but probably significant. So I guess that's kind of what you'd expect. Not too earth-shattering, but anyway, the point was not to do the analysis because I'm not really an expert on Australian elections, but more to show you how you can take the context as a data Docker file, the data in an open data platform, and the pipeline here, Yeah. So I guess to your point, Nick, the pipeline isn't all in the Markdown script because there's some stuff that happens before it, but you get the idea. Okay, so finally a machine learning example. Is everybody familiar with the MNIST data set, the digit recognition stuff? Yeah, where they collected, 40,000 pictures of handwritten digits. And it's a common, I think it maybe started off as a casual competition, but it's a common data set to use for kind of exploring machine learning and stuff. The Keras R package nicely provides the MNIST data set as data available in the package, so you can easily play with it. And so one nice thing about Docker is the ability to create images and then deploy them in different runtime environments. So one thing you can do, for instance, is let's see. I'm going to sign in here. So I have a pre-cooked EC2 instance. This isn't the speediest. I wonder if our competitors in the other room are hogging the Wi-Fi bandwidth. So anybody played with AWS much for running stuff? Maybe about half. Okay, so this will be a little bit familiar to you. So this is the interface on AWS where you can basically spin up instances of virtual machines in their environment. And they make a instance type called P2 that has one NVIDIA Tesla, the G10, I think, or something like that, installed in it. So you can have a GPU, and hopefully everybody's familiar with the fact that you can, when you do deep learning stuff and neural networks, and anything really that involves a lot of matrix manipulation and inverting matrices and stuff, those things run a lot faster, especially when they're large matrices on GPUs, because that kind of math is kind of what's necessary to manipulate pixels on the screen. So it turns out those chipsets and processors and cards are very good at doing that kind of math. So I know some people in the intro said you've had kind of weekend projects or whatever to build rigs in your basement and stuff, which is a great thing to do. But if you want to experiment with this stuff quickly and easily, you can just get an account on AWS. And running a P2 X large instance, which is going to be good enough to do experimentation with, is 90 US cents an hour. And they charge you 1/60th of that for the first minute, and then it's prorated per second after that. So, you just spin this thing up, you can see that I've got it stopped right now, and you can just start it. And it takes a little bit to come out. And then you can just SSH into this, and it's just an Ubuntu instance by default that I have modified and installed some stuff on. And while that's coming up, let me show you this. So if you go into my Docker repo on GitHub and go to the wiki, there's a page there called AWS EC2 Machine Learning Instance Setup. And here's all the steps you have to go through. So you might ask, why didn't you just put this in a Docker file after you've spent 3 hours talking to us about how great Docker is? And the reason is you have to have some stuff installed on the Docker host. In particular, you have to install the NVIDIA drivers that know how to talk to that card. And those don't come installed by default and configured by default on the EC2 instance. So there's no way to do that in a container because it has to be stuff that's available on the host. And as you can see, it's maybe not the easiest set of steps as those of you who have set this up on rigs at home can probably testify to. NVIDIA, though, does provide a Docker runtime. So if you go back to that picture of the stack, there was the run C box that's actually responsible for launching the containers. and providing them with their execution context. When you run NVIDIA's runtime, it replaces pieces of that with additional pieces that know how to access the GPU card and use these drivers to do so. So if you follow these steps, and this should work on your setup at home if you've done this, as long as you have the card installed. Nothing is magic here except for the first couple steps about EC2. But it's an easy way for, $1 an hour to play around with these things. And also, if you want to spend more, like $20 an hour, you can get an instance that has a cluster of like 30 of them in it. So as long as Keras and TensorFlow that Keras is using under the covers are properly parallelized, some of this stuff could actually fly pretty quick with it. Okay, so our instance is running. Let me grab the public domain name there. And so to SSH into AWS instances, when you create the instance, you create a key pair. And then when you log in, you have to reference the key pair. So this is going to be different. If you set this up, you'll have a different key pair, obviously. And then the user of the instance is always Ubuntu. And then the IP address, it's going to complain that it's never seen that IP address before, so I'm okay with that. And now I'm into this instance. So the instance I started up on EC2, I've just SSH'd into it. And in the wiki page here, I gave you a little thing you can run to test whether the drivers are properly installed. Needs to run in a container. That's concerning. It should already have the latest. Well, this will be interesting to see what this does. What I suspect happens is NVIDIA has published a new version of this image out there. And so, yeah. So I don't know why. I just did this last night. Well, let's see if my demo is how I wanted to run it. Hold on. Okay, so if we actually run an instance of R on this. Okay, so we're going to run it with the and then I created an image called, capture this somewhere. R Keras CUDA GPU. And it's CUDA with a C. Let me just see if removing the image that it downloaded will do it. I have no idea. Literally, I did just run this last night. What's that? Yeah. Yeah. Speed. Yeah, I don't know. Yeah. Well, apologies. It's a really cool demo. What you see when you run this is if you run the so the Arcaris, if we just do this locally, so this is an R image, and you're free to use this if you want, that has the TensorFlow and Keras stuff installed on it. So if you're doing things with machine learning, and then you can run the examples. If you go into here, these are a lot of good examples for illustrating deep learning and so forth. So if you just run the basic MNIST one, you can source this into your R environment. And you'll see it pull the data down there somewhat slowly. Okay, faster. And you'll see it go through each of the epochs of running the, fitting the neural net model. And it actually goes not too slowly on my MacBook here. A couple seconds per epoch, and there's 30 of them. But one thing, and this just absolutely flies on the P2 EC2 instance. But one thing that doesn't necessarily go so fast is if you run the convolutional neural network version of this, which involves a lot more math. It absolutely crawls here, but when you run this on a GPU, it goes just as fast as the other one did. Dang it, I have no idea why. I'm trying to think real quick why that didn't work. But anyway, probably not something we're going to fix in 5 minutes. So what I can do is so I have email addresses for most of you, but for those of you who stepped in and took the tutorial kind of at the last minute today, Nick, do we have a piece of paper where folks could write down their email addresses? If you want, what I can do is offer to do this, to do the demo that we didn't have time to get to, and this one on a Google Hangout or something. Or feel free to play with it yourself if you want to, but I'm happy to do that in a Google Hangout next week or in the next couple of weeks or something, and I can walk you through the rest. Google Hangouts are really easy. It allows for screen sharing, and you can do a presentation and so forth. So we do only have the 5 minutes. Okay, so here, let's put it up here, Nick. So if you've been getting emails from me, you don't need to put your email address on here. But if you haven't been, that means I don't know how to reach you. So if you're interested in that, put your email address on the pad up here. In the couple minutes we have left, any questions or things that you wanted to get to about Docker that we didn't have a chance to get to? Yeah. Yeah, it's so they're in two places. I have a repo on GitHub that's just scottgame/docker. So github.com/scottgame/docker. That's where I put all of my Docker images that I create for various purposes. And that's where the R and Keras stuff is. All the other examples are in another GitHub repo that's called shiny-docker-demo. And so the multi-container one is out there. The Docker Compose files to run all that stuff is out there. And none of those examples require anything special in your Docker host. In fact, you should be able to, oh, my fan's kicking on here because it's not happy doing all this now. You should even be able to run them in Play with Docker. So no special install instructions there or anything. But yeah, it's all out there. Yeah. Most of them, no. But some of them were kind of things building up to the other examples. So always feel free to email me if you want something specific about how to do something. The example of accessing the API through like HTTR and JSONLite, I had that in my speaker notes in the slide, and I just created that in a separate source file yesterday, and I haven't pushed it yet. But that'll be up there in that Shiny Docker demo repo as well, if you're interested in that. What else? Yeah. Right. I don't think terribly difficult. DockerHub has images for all the Hadoop big data ecosystem stuff. I don't have any personal experience with it, so I can't sort of give you pointers on that. But I don't think it would be difficult. It's sort of like any other data access mechanism. So your Hadoop file system will likely be external to, it'll be living on the host, or actually accessible via the host on multiple nodes. And you just bind mount that stuff into your containers is probably how it does it. But again, I'm a little out of my depth here because I haven't done it personally. But I don't think it'll be difficult. What else? No, so the question, actually, I should have been doing this because they're recording these. So the question is, where's Docker going? Is it going to mature further? I think you're right. It is quite mature. Looking back 2 years ago to where it was, it's miles ahead now. If you look at kind of the marketing that's coming out of Docker.com, they're really pushing their enterprise edition stuff and the additional features that has, which I'm actually really unfamiliar with because I don't really, I've never really used it. But Linux containers and namespaces and C groups have been in the kernel for 15 years now, and I don't think there's really a lot of innovation in that space. So the kind of core technology is there, and it really hasn't changed much. They added user namespaces like 4 or 5 years ago. It's really not changing much. I imagine they're getting feedback from the user community about things. The Moby project is actually something really interesting to look at as they continue evolving. Docker used to be kind of a monolithic stack, and the Moby project has broken that out into pieces so that they're more pluggable. Like 3 years ago, the NVIDIA stuff would not have been possible, or at least not possible as easy as it was for NVIDIA to do it, because all they needed to do was replace this one piece. They didn't have to rebuild the whole stack. So there may be some continued evolution of that as they find ways to break it apart, modularize it more, and then just some usability improvements. That's my sense of it. Any other questions? All right, so apologies that the 2 demos at the end, the big finale and the fireworks, were a dud. They didn't light. But again, I'll make it up to you if you're willing to attend a webinar in the next couple weeks. More than happy to do that. I can even do a couple of them. We'll arrange time zones and stuff so it works for everybody. But hopefully you got something out of this, and I'll be here all week, as they say. So feel free to track me down. I look forward to talking to you more. Thanks a lot. Appreciate it. Yep.